Signal integrity problems on the PCB can easily be located and fixed using hyperlinks. After exporting your design, you can run simulations either in batch mode or interactive mode to identify any potential signal integrity issues. The built-in terminator wizard can analyze the topology and suggest the optimal termination. And you can then see that terminator in action directly in board sim using the quick terminators function. You can also export your signals to line sim for even further analysis. So let's take a quick look at how to identify and address signal integrity issues at the board level. In hyperlinks, you can analyze all of the nets on the board using batch analysis, which generates a results spreadsheet, report and waveforms. You can also analyze individual nets interactively. For example, if I take a look at this clock net and run a simulation on it, we will find that it has extremely poor signal integrity. There are massive overshoots which would cause damage to the receiver, in addition to very large ringbacks, which would cause false switch-ins. In order to address problems like these, Hyperlinks has a terminator wizard, which automatically identifies the proper termination for a net. I can apply the suggested terminator value directly to this net by selecting Apply Values and then resimulate with the terminator in place to see the results. The results are very dramatic. What was a horribly distorted clock signal is instantly cleaned up with the addition of the series termination resistor. Since the terminator was added in board sim on a completed layout, the terminator added to the simulation is what was referred to as a quick terminator. This was added to the driver along with a short length of trace to mimic what would need to be changed in the layout. In this case, a 100mm trace was added on layer 3, the first signal layer. So if I wanted to see what a 1/2 inch trace routed on layer 1 would look like instead, I can make that change here. When I simulate with a new trace route, we can see that there is more noise added to the waveform, but it still looks like a satisfactory clock signal. Further what-if exploration can also be performed in line sim. If the signal is exported to line sim, it will appear in schematic form, where I can then modify the different traces, vias and discrete components. Here you can see the trace and resistor I added in board sim. That also comes through to the exported schematic. I can use the sweep manager to try a range of values for all the different parameters in the schematic, such as resistor values, trace lengths and widths, and buffer models. Here I will test a range of resistor values from 30 to 70 ohms in 5 ohm increments and then look at the results. In some cases it looks like the timing margin is greatly reduced on the falling edge. If I zoom into the area around the lower logic threshold, around 800 millivolts, we can see that a resistor value around 35 ohms will have very little impact on our timing margins. However, if I scroll down to the area around 0 volts, I can find the resistor values which will give us near zero overshoot. It looks to be around 55 or 50 ohms. By sweeping different resistor values, I can find a value that gives a good balance between timing margin and overshoot. Now you've seen how easy it can be to eliminate signal integrity issues from your design, you can appreciate how hyperlinks can give you the confidence that your design will be done right the first time, saving you valuable time and money in your design cycle.